Today's session is from Edge Impulse. And with us today for this session is Jongboom. He's the co-founder and CTO of Edge Impulse, the creator of leading development platform for running AI at the edge. Jan is going to address a difficult challenge. What happens when you train your computer vision model to detect a set of objects, but a new object appears? What then? Does it just get misclassified? We're going to find out. So with that, let me introduce our speaker, Jongboom.
Thanks so much. Awesome. Hello, I'm Jan. Good to see all of you in here. So, listening to some of the tracks, a lot of it is about, I have a model and now I want to run it on hardware and run it faster and whatnot. But someone needs to create these models. And that's where Edge Impulse comes in. So I used to work in the silicon industry, looking at how can we make faster runtimes, better silicon, whatnot. And no one was addressing the question of, who is building these models? How are we actually training a model that can detect real use cases? So I started Edge Impulse together with my co-founder back in 2019 as an easy-to-use platform to use data to make informed decisions. And machine learning is one of the parts of that. I don't really care how you get the insight in your data. If you use signal processing, classical ML, or deep learning, I just want to help you build solutions that take real sensor data in and then draw real conclusions out. You can use it for free. You can also pay us if you like. I'd rather have the second thing, but as you can see from this graph, a lot of people, hopefully a few people here in the room, are just using Edge Impulse as is, as a free developer platform, still to build real solutions. So you can go all the way from zero to production on the free tier. Just as an indication of how popular it is, about a year ago at the Embedded Vision Summit, we were at 85,000 projects on the platform. Today we're at 185,000. And that is over 100,000 new projects being created on Edge Impulse, 40% of which are actually computer vision products. And 60% is radar, audio, current and accelerometer data, sensor fusion, and all kinds of stuff. But all right, so coming back to computer vision. Back in 2018, I was in Kenya. And I was doing deployment of camera traps in a conservatory at the Dekot University in Nyeri. And we wanted to show the students at the university kind of what you could do with computer vision models actually in the field. And we figured, well, we have a big conservatory with lots of African animals running around. Let's go count these animals. So we built something actually in a Raspberry Pi, put a little case around it, ran the model. Next day, we went into the conservatory to actually retrieve the devices. And lo and behold, according to our camera trap, we have seen a giraffe. And I knew quite a bit about the conservatory, or I didn't know a lot about the conservatory, but it did very much know that there was no giraffes out there. And the reason was we trained a model on Eastern African animals, but they actually had a llama in the conservatory. True story. There's a blog post from Damon Sivin about all of that. And that's often a problem, right, that we have when we're building computer vision models. So if we want to detect every animal in that conservatory, well, now I need to go collect examples of how that animal looks like, right? Lots of pictures of giraffes and lots of pictures of zebras. But then also I need to create this negative, this unknown class, which is every other object on Earth, which is impossible, right? I cannot get photos of every other object on Earth, and that's really problematic. So if you think about these relatively simple computer vision cases, right, detecting animals, I can probably come up with a pretty good other class, everything that's not a giraffe or a zebra. But if you're looking at real applications, someone is deploying something in a factory or on a production line, you often have lots of data set asymmetry. You probably have 1 million examples of something that looks good, and then very, very few examples of stuff that looks wrong. And thus making this negative or this unknown class is really problematic. And it gets even worse if you think, well, all my fault data is probably not a single class. It's probably, in this case, 3 different fault states. And it means that my asymmetry in my data set gets even bigger. Lots and lots of good data, very, very few examples of fault states. And there's probably a bunch of cases that your model, that stuff can fail that you actually don't know about yet. So, problematic. So how do we fix that in kind of non-vision cases? So we use a technique called anomaly detection. In essence, what we try to do, let's say that we're doing something with sensor data, so relatively low dimensional data, no computer vision. We create a 2D space of all potential inputs. We put all of our training data in there, map that to the 2D space. And the moment that we have a new sample come in during classification, we look, okay, where would this fall on this 2D matrix? If it's inside a cluster, then we know that it's not an anomaly. If it sits outside a cluster, then we know that that is an anomaly. And this works really well for low resolution sensor data, but not so much for images, right? Images is very high resolution data. A typical thing that we try to do with, for example, accelerometer data is say, hey, what are the key frequencies? Let's say they have a rotating fan. Okay, well, I see that this fan is rotating 40 times a second, so we need to see a peak at 40 hertz. If that peak is no longer there, then, well, it's probably an anomaly. Something weird is happening. If we think about anomaly detection in the context of computer vision, we sort of go to this idea of autoencoders. This was a couple of years ago when I started looking at what can we do around visual anomaly detection. This was sort of the rage. Simple concept. You have your input image, you have an encoder network, you have a decoder network. And then to see if you have an anomaly, you just compare the input and the output. And the theory, at least, is that if the network has learned a good representation of your data, it's probably already in your training set. So the difference should be small. And if you have something completely new, something completely novel, then the difference should be big because it cannot properly encode that in the network. However, they don't really work. So on one hand, they're really computationally expensive because you need both that encoder pipeline and the decoder pipeline, so you have twice the network. Working in pixel space, it's just really annoying. Like if you want to do a diff between things, you're just comparing pixels. So if something is shifted a little bit to the right or to the left, all of a sudden you can't recognize it anymore. Also, autoencoders typically lead to very, very blurry images because they're not penalized for stuff that is not very nicely recognizable. And it requires very high resolution images. And combined with kind of the computational expensiveness of this, makes it really, really, really expensive to run things. So we started thinking about how can we do something better. And just as a comparison, the new approach that we had, to get the same accuracy, we needed about 3 orders of a magnitude less parameters to get the same accuracy as we could do with autoencoders. And you can see from this, right? Like if that is the difference in the number of parameters, you can do, there's a very constrained set of things you can do with autoencoders that you can do with our new approach, FOMO-AD. So as I said, anomaly detection on sensor data, the way that we approach that is we take our inputs, we run it through a DSP algorithm, for example, to look at what the peak frequencies are, and then we train a clustering algorithm on those features. So I might train a clustering algorithm on the root mean square of the motion on the z-axis on my accelerometer, on the x-axis, and then on the spectral power between 33 and 35 hertz, because I expect something to happen there. Now, naturally, that doesn't really work on images. And the reason for that is that, well, if you look at a typical image, 320 by 320 by 3 channels, that is 300,000 and a lot of pixels. So try put that many axes into a clustering algorithm, right? That's not going to fly. So we thought, okay, well, what can we do to make this not run on pixel space, but rather on something more that has more information, but has actually less features. And we came up with the idea to actually use neural network embeddings. So the idea is we take a neural network, for example, MobileNet, and we run your image through MobileNet. Then just before we're actually doing the softmax, that's the moment that we cut off the network, and then we look at what the embeddings of the neural network are. These are learned features about your data set. Right? We don't really know what they are, but there's probably stuff around contrast, shapes, shade, whatnot, that is learned internally. And that is on one hand a lot less features. So we go down from like this 300-something thousand features that we have in pixel space to maybe 1,200 features. And they're much more specialized. They don't really care about pixels or where something is in the image. It might be something described like, hey, I see a circle somewhere here. That might be one of the features actually learned. So through that, we can actually throw this through one of these clustering algorithms. So in our case, we use Gaussian mixture models, but you could use a k-means clustering or typical classical ML clustering approach with that. So yeah, this operates on feature space, not on pixel space, which I think is an important distinction. So you might say, Jan, that sounds sort of like it might work. Does it actually? So here's an experiment that you can do today. So take 3 objects in your house or wherever. So I took a Coke can, my piano, and my Apple Watch. Run it, take a pre-trained neural network. In my case, I took MobileNet v2. And just take the embeddings. So I ran this all the way through just before the end, I cut it off, took the embeddings of all of these things, and then I ran it through a dimensionality reduction algorithm. And here we go. Super clear clusters of 2 things, or 3 things, right? So my piano is one cluster, my Apple Watch is a cluster, my Coke can is a cluster. Are these in MobileNet? I have absolutely no idea. But it doesn't matter, right? Like these 1,000 classes that it knows, I don't care about them. I just care about the embeddings, about the learned representation of these features. Now the magical thing is that when I add new objects, so stuff that is neither my piano, neither my Apple Watch, and neither my Coke can, and that's the stuff here in the gray, all of a sudden I see that these fall outside of these normal clusters. So here I have a photo of my plant, and here I have a photo of my team. And the amazing thing is that you can train a logistic regression model to divide these clusters, right? And the amazing thing is that that is something that we can do to check on visual anomaly detection as well. I can just train on all my normal training data. I can take a pre-trained neural network as my feature extractor. And after that, I can just use a clustering algorithm to see, does it fall inside any known clusters, yes or no? If yes, that's fine. This looks like training data, not an anomaly. If it falls outside, definitely an anomaly. All right, so let's try that out. So then a secondary thing. Okay, so this works on complete images, right? So I can throw a complete image in. Does it look like anything in my training set? Yes or no? But very often we also want some locality. So where is the anomaly? Concrete use case, let's say that we have a really big wall here, and there's a crack somewhere in the left top corner. And a photo of this wall might be 3,000 by 2,000 pixels, and the actual crack might be 1% of that image. So I can't treat the whole image as anomalous, because that's really hard to get my loss function right if I have so little fault data. And then the second thing is, it would be really useful to know where a fault is. So I don't need to train my technician that the algorithm says, hey, there's a fault, and he needs to zoom in to this little corner and then find that actual crack in there. So okay, so how can we do that on top? So if people have been here last year, you might have seen that we've released FOMO, faster objects, more objects, which was a novel architecture to do object detection on really constrained devices. And the way that we do that is that we actually train a whole bunch of classifiers. So we sort of get a segmentation map over your input image. So we put a heat map over that. And each cell of this is a classifier. So if I want to train this on these Jenga blocks, then these will probably be the activations. And from that, I can just draw bounding boxes around it, or I can look at the centroid of this data. It's a really useful approach for stuff where you don't have overlapping objects and objects that are relatively the same size. Mostly because this can be implemented really, really efficiently. This is essentially a free add-on to a convolutional neural network. So we came with this idea, well, if we have this already working for classifications, what if we replace that classification hat, that classification per cell, with a Gaussian mixture model? Now we get locality as well. Now we understand where the anomaly is and if something is anomalous in this image. So the way we've done is here, we've replaced each cell with an anomaly detector. The cool part is that we can now train this on non-anomalous data. So let's say that here I'm only training this on the Jenga blocks and on the background. That's all the stuff that I train about. I never give it any examples of negative data. And the advantage is that it's incredibly fast. So as I said, faster objects, more objects. That's our object detection algorithm for constrained devices. It actually runs 30 frames a second on a Cortex M7. Like really, really small, runs at under 200K of RAM. So our new work on FOMO-AD, so the anomaly detection version of this, runs with a similar performance profile, which I think is really awesome. So here's a demo of this. So I have a Ready Robotics robot arm that's going to swivel with a bell of sensor on it. And then I've trained this on 150 images of just the Jenga blocks and the blue background. I haven't given it any other examples. And I'm using MobileNet embeddings just as is. So I didn't train a secondary neural network as my feature extractor. The darker the cell, so you see the cells on the left, the darker the cell, the less anomalous it is. So the lighter, the more anomalous. So everything that's an anomaly should light up really, really quickly, or really, really proficiently. So we introduce a red cube, never seen that, lights up. Removing the red cube, okay, back to normal. Introduce a green something, 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 and then we'll know what it is. Lights up immediately. Take that out, and now I put a hand or something else that is never seen. Super clear. That is definitely an anomaly. So really cool. So we sort of get this for free, and this runs on a Raspberry Pi, I think 60 frames a second or something, and a 160 by 160 pixel image, outputting a 20 by 20 heat map. So here's some performance numbers. So we can make this really, really small by saying I take a small feature extractor, right? So it might take a 96 by 96 MobileNet model. I can run it actually in real time, 30 frames a second on a Cortex M4. If you take something really beefy, like my MacBook, with a proper accelerator, I can do 1,000 frames a second on that. Naturally, this means that you have a lot of excess power to do really big images, for example. Another example, so here's a quality assurance on cracks, like the example that I showed before. We throw this through, and this is a small cutout of a much larger image, and it immediately lights up the stuff where there's not normal data. There's a crack in that, so immediately see that. Another one, just because it's almost 5 o'clock and we can go drink beer here, is an example of production line monitoring actually shot at my house. So I have a video here. Same thing as we did before. So we have the heat map there. And it starts off with actually 2 Heineken bottles. And that's what it's being trained on, just on the Heineken bottles in the background. And now I'm going to add a different beer bottle. There we go. And that immediately lights up, telling me that is definitely an anomaly. This is something that I've never seen before. So really powerful stuff. Okay. So you might think, well, Jan, this sounds too good to be true. Like, where doesn't this work? Because these are really nice cherry-picked examples that you gave us. Stuff where it doesn't work. First of all, if you use a pre-trained feature extractor, like, for example, MobileNet, it works really well on stuff that is in ImageNet or looks like things that would be in ImageNet. Stuff like photos from a microscope or something does terribly. The nice thing is you can use a different feature extractor. So you might train a classification model and then use that feature extractor as a way. That's a nice way around. The second is that we have this, to create this heat map. So we have, let's say, a 160 by 160 pixel input. Then we create a heat map, which is 20 by 20 pixel output. And then every 8 by 8 pixel input of your original image maps to one block in the heat map. That's sort of your receptive field, and you can tweak that. So you might say it's 8:1, which is default, or do 4:1 or 2:1 if I want to have really, really small images. If you throw something at it that is much larger than the receptive field, like I put this bottle in front of it, it starts performing really badly. So we always recommend actually deploy 2 models here. One classifier that detects, do I think I see it? And then another anomaly detectors, like, can I trust the neural network classifier, yes or no? And it's fully convolutional, so stuff that convolutions have a lot of trouble picking up, like things with lots of noise, it's really bad at. And you might think, well, my images don't look like that, but we've seen cameras fail in non-obvious ways, and sometimes with really noisy images. And you might think, well, that's stuff that I would like to pick up, because that is an anomaly of the sensor here. That stuff we're not really good at picking up. So, all right, so what have we learned out of this? So first of all, embeddings have a large number of dimensions, especially if you have a really high resolution input image, right? So if you take a 96 by 96 pixel MobileNet model, you get some 1,200 something features out. That's still fine. But if you scaled it up to 1024 by 1024, it's fully convolutional, so the number of features explodes. One thing that we've learned is actually that we can do random projection on these. And that actually works really well with a small effect on accuracy, but it reduces the complexity of the model significantly. Second, because you have these embeddings, you can actually share these. So if we train a classifier, then we can take the embedded, then we can run the whole model up until the last layer. Those are the same embeddings we use for both the classifier and for the anomaly detector. So we sort of get the anomaly detector for free, which is really cool. The anomaly detector is also really simple because it's just a Gaussian mixture model or a k-means clustering algorithm. So you can actually fine-tune that on the edge. So something we've done is say we go in calibration mode for a day. We snap 1,000 photos of stuff we've seen, calculate the embeddings. That's actually the input for a Gaussian mixture model. And now when new stuff is introduced to the camera, it actually uses that locally trained, locally fine-tuned anomaly detection model, which I think is really, really cool. And then last, if you want to do custom code to a neural network graph, like what we do here, something that doesn't look like a neural network, but you still want to have it in a graph, go take a look at JAX. I absolutely love it. It's basically a Python to compute graph compiler made by the Google team. We use it for a lot of stuff, pre-processing, post-processing of things. So if you're interested in that kind of thing, go take a look at that. Absolutely amazing. With that, I want to thank you all for paying attention for 20 minutes to me in this incredibly hot room. And encourage you to go look at our booth just outside or go to a Amir session.
Thank you, Jan.
Thank you.
Great presentation. Great presentation. Thank you. Hey, we have a few minutes for Q&A, so if you have a question for Jan, please step up to the mic, and he'll answer your question.
Yeah.
And until so, I'm going to ask him a couple of questions. So the FOMO is free for developers? Okay,
Yes.
so how do you stay in business?
Yeah, so we have, I like to say, it's either free or expensive. And then Spencer, my CRO, says, no, not expensive. No, it's, no, so yeah, it's free. People can use it. But then we have an enterprise version. So there's some limits, like a 20-minute training limit. So if you need to do more, then our enterprise license comes into play.
Okay, great. Okay, so one other question, I guess. Can you apply this approach to non-image data?
Yeah.
Maybe you could talk a little bit about that.
Yeah, absolutely. So we actually started doing this on non-image data. So this idea of anomaly detection, that was in Edge Impulse from the get-go because I just didn't understand. Every time, like look at any of the demos here, right? Any classification demo. Do something unexpected, and it will give the wrong result. And I could not understand why it is such an overlooked feature. So from the get-go, we started having anomaly detection on, for example, accelerometer data. So if you do gestures and then you do something weird, then we actually tell you we can't trust the neural network. And I've really wanted to have this for computer vision for such a long time. So very happy with what our ML team baked up.
Okay, great. All right. Any other questions? No? Well, let's thank Jan for his presentation. Great job.
Thank you all for being here.
Yeah.